All right, so moving into the outer solar system, talking about these things that we call Kuiper Belt objects, kind of gets us back to a brief reminder about Pluto's status. Of course, we did think of Pluto as a planet. It's a bit smaller than Earth's moon, but it was larger than any other known Kuiper Belt object for a while, until we started discovering even larger Kuiper Belt objects like this Eris in the upper left-hand corner. And that was maybe around a decade ago, so that was sort of the point where people started talking about, well, what are we really going to do here? Are we going to have another planet called Eris that's much farther out, or are we going to actually kind of acknowledge the fact that Pluto is just kind of an accidental planet? You know, it's really a Kuiper Belt object. It's just one of the more nearby ones. Okay, so again, cometary bodies, we're going to form the tail when the object gets close to the sun, and here again we see the two kinds of tails. We see the dust tail has a curved shape, the ion tail has a straight shape. Okay, so what's going on here is that you basically have this icy nucleus that's a few kilometers across. It's actually very low density. It's kind of like the density of a snowball or something like that, but it's a few kilometers across. It's ice, it's methane, some water, ice, mixed in with small bits of gravel, you know, rock, and lots of dust, things like that. So what happens when we see the comet start to sublimate? Okay, so the ice is just disappearing as a vapor, right? So what's left behind? You're going to have some of those dust particles and small gravel-type particles, but you're actually also going to have subatomic particles, which are ions that get released in the process of the sublimation of the gases. Now the ions are microscopic objects, so they have very, very little mass. So an ion is pushed right out by the solar wind of particles that come from the sun. The ion is very low mass, has no ability to resist that push that the sun is giving it through the solar wind. So the ion tail is always going to point straight away from the sun. Those little ions have no way to resist the push of the solar wind, so they just get blown straight away. The curved tail represents the shape that we get when we look at the tail that's composed of these dust and small gravel particles. Those things, as small as they are, still try to orbit the sun, and because they're significantly more massive than the subatomic particles, they're actually able to resist the effect of the solar wind to a limited extent, and that's why you get this curvature. The particles are trying to go into a curved orbit around the sun, and they're partially succeeding because they're just a little bit, they're massive enough that they can partially resist the pressure of the solar wind, but not completely. So you basically still have a tail pointing away from the sun, but with a little bit of curvature because these particles, again, you know, we're not talking about large rocks here, we're just talking about dust particles and small bits of gravel, but they're able to, you know, partially resist the effect of the solar wind. So that's why we have the two tails. Ion tail, subatomic particles, straight away from the sun. The whitish tail, curved tail, is the dust tail. Okay? All right, so back to the coma. We have the coma. The nucleus is in the dead center. There's actually a little bit of information now about what the nuclei of comets look like because we've actually sent missions to cometary nuclei over the last 15 or 20 years or so. We can talk about that a little bit. And notice again, the direction to the sun is the opposite direction from the tail direction. All right, so starting to talk a little bit about the material in the next chapter regarding the formation of the solar system as a prelude to that. When we start to talk about the Oort cloud, we believe that we're talking about protoplanetary icy bodies, which probably formed in the inner solar system, well actually what we would call the outer solar system really, like Saturn to Jupiter's type of distance, which then interacted with the giant planets, primarily Jupiter, and were actually flung by kind of a gravitational slingshot effect out, way out of the solar system, almost with enough energy to completely escape from the solar system. In fact, some probably did completely escape from the solar system. But the ones that completely escaped aren't in the Oort cloud because they're gone. They escaped, right? So they're not in the solar system. But the ones that don't have enough energy to escape tend to cluster in this outer zone that we call the Oort cloud. So again, we have the long period comets living out there in the Oort cloud. The objects in the Kuiper belt, we think, represent the native radius from the sun where they actually formed in the first place. Okay, so when I say when they formed in the first place, again, looking ahead a little bit, we think everything in the solar system formed from a single disk of completely ionized gas, completely vaporized gas, nothing solid at all, just a gas, which gradually cooled. And when it cooled, what you get would depend on how far away from the forming sun you were. Okay? If you were farther away from the forming sun, it was cooler, and you could get these icy bodies. Closer in, you tended to get the rocky bodies. This is the beginning of that solar system-wide differentiation I keep talking about, where you get the rocky stuff near the sun, icy stuff farther away. Okay, so the Kuiper belt was basically the sweet spot for ices to be able to form. So when we look at that solar nebula that we'll talk about, it was able to freeze out. Sorry. Oh, I just connected? No, I did this. Sorry. Clear. So continuing the transmission. Right, so at the distance of the Kuiper belt, we're able to get these ices to form. So they formed there, they stayed there, they lived their whole lives in the Kuiper belt, unless they get perturbed and they fall into the inner solar system and actually form a comet that we would call a short period comet. Okay, this is actually a very difficult mission. This is actually the first example of a ruler flown in space. This is an early model. They pulled it up alongside, and we're actually able to directly measure the length of this cometary belt. You see the scale in kilometers down there. Talking about several 100,000 kilometers across. Again, that makes that coma sort of about the size of Jupiter or Saturn. Again, there's the ruler. Very difficult maneuver. Don't try this at home. I don't know what's going on there, but anyway. This was done by professionals. Okay? Where NASA had a pretty good budget, by the way. They could never get away with that anymore. All right, this is an example of what you can get. You can get some strange-looking configurations when you look at that dust tail real close up. This is actually a shot taken from a space mission. And what you see are a little bit more detailed than we could ever see in those distant photos. So notice that we have this kind of spiky configuration, which is the ion tail blasting straight away. And then you have that wispy, almost corkscrew part, which is the dust tail forming. So when you really zoom in, it's kind of a chaotic process. It's not quite as smooth and beautiful as when you look at large distances. And it apparently is telling us that different parts of that cometary nucleus are sublimating and forming this gas in different ways, right? I mean, if it was all the same, you'd see kind of a homogeneous, blob of stream of gas and dust coming off. But that, I did this to make myself that time, so I'm getting very demonstrative today for some reason. Okay. I won't do it again. Sorry. I'll try not to. Yeah, please. Nothing further. Okay, so anyway, the structure that we're seeing there is telling us that this cometary nucleus, this icy body, is kind of blowing apart in an asymmetrical way, not a completely smooth way. So that's an interesting thing to see. Beautiful example of the dual tail, comet tail bob. There you see the ion tail, dust tail, very nice. 1997, one of the classic comets. Another shot. Good postcard shot there. Another one. There you go. It didn't really change direction that much, honestly. It didn't really do that. Okay, so picking up on cometary nuclei again, so we get the ion tail straight, the dust tail curved. Already talked about this because of the interaction of the sun's gravity with the massive, quote-unquote, massive dust particles. Halley's is the cometary nucleus that actually had been visited very close up in the mid-1980s by a European mission that actually was able to get close enough to make it through the tail. And remember, this is a lot of gas and dust and rocky debris and stuff. It's not necessarily the easiest thing to do to actually get close to a cometary nucleus when its tail is blazing away. And that's what happened, because this was done in 1986, which is when Halley was close to the sun and had the tail. So we have this whole business going on, comet shrouded in material. And when we get close, we see that indeed the cometary nucleus is jetting off vapors and dust particles in a very asymmetrical way. Okay? So, in fact, we see even jets of material coming off the comet. And those jets of material are, again, very asymmetrical. Parts of the nucleus are darkened by radiation exposure in deep space. Parts are just blasting off this sublimated gas. The actual force of that sublimated gas is so strong, it actually forms a kind of a jet that keeps the nucleus spinning and can even alter its orbit. So it turns out that when you discover a comet, you don't necessarily know exactly where it's going to be forever in the future, like you generally do with planets, because the comets that go close to the sun end up with this kind of jetpack on their backs, and the sublimation happens in a completely unpredictable way. So you end up with the orbit actually being affected by this jet effect, and that makes it much more difficult to predict cometary orbits over many cycles. Okay, so we have this crust of the nucleus that's radiation darkened, the icy interior, of course, and then these jets indicate the areas where sublimation is actually occurring. Okay, so what's the nucleus composed of? Primordial ices, the typical types of ices that we see in the outer solar system. Water ice, methane ice, and ammonia ice. The common constituents that we've already talked about in bodies like Pluto and the moons of the outer planets, and even when we're talking about Neptune, we see methane out there. So that's a very primordial composition, and our ability to visit comets and sample their structure gives us a way of taking a snapshot of the primordial material that was there 4.5 to 5 billion years ago. Now, how primordial is primordial in this case? Because there's different levels of primordiality, if that's a word. You know, if you look at an asteroid, you're not necessarily seeing a completely primordial object, because asteroids sometimes have iron in them. That indicates they were part of a larger body that got blasted apart. So that's not primordial completely. It was reprocessed. Comets are in a whole other class because of the ice composition. If you look at a comet, you're seeing ices that couldn't have been reprocessed, really, because if it was part of a larger body, the pressures and compression would have just melted that ice. So comets are the most primordial objects in the solar system. And okay, sorry, one thing I forgot to mention, the density is very low, 0.1 gram per cubic centimeter, so it's like a very porous kind of ice. Again, probably similar to the density of a snowball or something. Not a nasty old ice ball, but a fluffy snowball probably would have around the density that we're talking about. Okay, so comets go through a life cycle, if they actually get into the inner solar system, because the sun will cause them to sublimate and lose some of this icy glue that holds them together. And what we get, once we've eliminated the ice, is a kind of a flotilla of debris that keeps following the original comet's orbit forever, because we're talking about the massive enough stuff that doesn't get blown away, the particles of dust, the particles of rock, they're going to follow the original orbit, and then that actually represents swarms of meteors, because the Earth can pass through that cometary debris that's left over. It's not like we're talking big asteroids, it's all small stuff. But if the sun passes through the trail that we're talking about, we get meteor showers. And this is typically the reason that we get the periodic meteor showers that we do, like the Geminid meteor showers that we're having in early December, are actually, again, remnant cometary debris that we basically see the same time of the year, because of course the orbit is an annual type phenomenon, so we go through that area. It's better some years than other years. Okay, the reason for that is because we're going to go through this primordial orbital path the same time every year, in December, let's say, for the Geminids. But we may not pass through a thick bunch of debris that particular year. So, you know, you might get a real heavy Geminid meteor shower, or you might get a real wimpy one. It just depends on how close you are to these regions where there's a lot of junk. Now, why would it be lumpy like this? Probably represents periods when the comet, chunks of the comet completely fell apart. So, historically, a big chunk of the comet fell apart over a period of years there. And likewise, each of these accumulations represents kind of a catastrophic event in the life of the comet when a bunch of it fell apart and sublimated.